So now I want to talk about a new model and a new kind of bifurcation. So we're continuing our tour through the zoo of bifurcations. And this is an interesting new kind, and it's an interesting new model. And it's a model of public opinion. And incidentally, I'm following a beautiful paper by Thomas Lux, which is in the Economic Journal in 1995, called Market Bubbles and Crashes. And that's what this is a model of. It's how do bubbles and market crashes happen. So in this model, this is what is called, and I think this is really our first real example of this, is a compartmental model. And in a compartmental model, we have compartments. And for this particular situation, we're going to have two compartments. And Lux was interested in modeling stock market crashes and bubbles. And so the two kinds of compartments we have, the two kinds of people we can have, he called them negatives and positives, basically speaking bears and bulls, people who think the stock is going down and people who think the stock is going up. But this could be sort of any negative, positive, it could be anything. It could be Democrats and Republicans, it could be whatever. And in a compartmental model, we write down the two compartments. This is the N compartment and the P compartment. And then we ask the usual questions. What contributes to the N compartment? What detracts from the N compartment? What contributes to the P compartment? What detracts from the P compartment? And these four arrows that I drew, these would typically be birth and death, or birth and immigration. This would be death and or emigration, birth and immigration, death and emigration. All of those are possible and would have to be in a complete model, but we're going to look at this over a shorter term behavior so that basically no one dies. There is no death term in our model, and there is no birth term in our model. The only changes that are going to occur in our model are the changes from N to P and the changes from P to N. So in that respect, it's a lot like a chemical reaction. So we have people going from N to P, and we're going to call the rate of that K N to P. And then we have people going from P to N, and that rate is going to be K P to N. So from this compartmental diagram, we can directly write the differential equation. The differential equation is n prime equals what makes n go up minus what makes n go down. What makes n go up is p's converting to n's at a rate kpn. So n prime equals plus kpnp. That's the p's converting to n's. But then what detracts from n, what makes n go down, is n's converting to p's. And the n's converting to p's is just knp times n. Similarly, p prime is just going to be the opposite. P prime, the positive term, is knpn, that's the n's converting to p's. And the negative term is the p's converting to n's, which is kpnp. So there is a nice differential equation in the two variables n and p. Now, of course, we haven't specified what these constants are. In fact, they're not going to be constant. But what these transition probabilities, and that is a way to think about kpn and knp, by the way. These are the transition probabilities or the transition rates from n to p and from p to n. So we have this box model, as it's called, and I'm putting n over here and p over here, and that's k n to p, and this is k p to n. So we have this two-variable differential equation, but you'll notice something. If there's no birth and no death, and in this first pass at a model, there is no birth and death. If there's no birth and death, then the total population is constant. And that means that the total population is, in this case, n plus p. And we're saying that n plus p is a constant. And for reasons that'll become clear in a minute, I'm going to define that constant as 2m. So 2m is the number of people. And now we want to use this to convert this two-variable differential equation into a single-variable differential equation, because we love single-variable differential equations because we can study them with very special methods. So how are we going to convert this to one variable? I'm going to define a single variable. And the variable I'm going to define is x. And I'm going to define it as p minus n over 2m. Now, what does that mean? So what it is the imbalance of positives over negatives. So we're going to call this the imbalance toward positivity. Notice that if p equals n, then we have an equal number of positives and negatives. And in that case, when p equals n, x equals 0. So x can be negative if the negatives outweigh the positives, or x can be positive if the positives outweigh the negatives. So that is our new variable. And now we need to use that new variable to convert this two-variable equation into a single variable equation. So first of all, if x is equal to p minus n over 2m, then we can just differentiate that expression and say x prime is equal to 1 over 2m times p prime minus n prime. Now we know what p prime and n prime are. We get them from right there. And let's put that in. 1 over 2m times knpn minus kpnp, p prime minus n prime, minus kpnp, minus minus is plus knpn. So what have we got here? We have plus knpn plus knpn. So let's just have a 2 there. And then we have minus kpnp minus kpnp. Let's have minus 2 there and take that out also. Now we can get rid of that 2. And we have 1 over m knpn minus kpnp. p, and that's x prime. So that's great. Now we need to operate on, we need to find out what KNP and KPN are, and then get N and P out of that equation in terms of x, which is what we will now do. So we're making progress in laying out this differential equation, and I remind you of this variable x, which we defined as p minus n over 2m, basically the imbalance towards positivity, the imbalance towards p. So now we have the beginnings of a differential equation for x, but we still have a lot of non-x terms in there, and we got to get rid of them. So the next question is, what are we going to say about KNP and KPN? So first of all, they're not constants. KNP, that is the transition probability or the transition frequency or the rate constant, if you will, of transition from negative to positive, is going to depend on the imbalance towards positive. And we're going to assume here the shape of this function is going to be an increasing function of x. And we're going to assume that, in fact, this KNP grows exponentially with x. And we're going to assume a model in which KNP grows exponentially with x. We need to just put a constant in front of that, but that constant's going to drop out in a minute. So KNP is an exponentially growing function of the imbalance towards positivity. So the name for this, it's often called the bandwagon effect. And for those of you who don't know what bandwagons are, people under 100 years old, the idea of the bandwagon effect is the more people that are on the bandwagon, the more people want to join the bandwagon. And so it's a positive feedback kind of term, which you see from the shape of the math. And this is postulating a bandwagon effect. And that parameter, which is going to be our important parameter, is just going to be the strength of the bandwagon effect. Now, conversely, we need a KPN, and that's going to be the transition from positive to negative, and that also needs to be a function of x, but it needs to be a declining function of x. And so we're going to assume e to the minus ax, and again we need a constant in there, but we're going to assume that KPN is a negative bandwagon effect, that the more people are are positive, the imbalance towards positivity means fewer people will be transitioning from out of P to N. Okay, so that helps. We now have KNP and KPN in terms of x and parameters. So that's great. Now we just need to get N and P out of there, and to get N and P in terms of x. And in order to do that, we just need to do a little algebraic manipulation. So let's remember what x is. Remember the definition of x. It's p minus n over 2m. And so now I'm going to do something funny, but you'll see why it works out so nicely. So what is 1 plus x? 1 plus x is going to be 1, which I write in that form, plus p minus n over 2m. So that's equal to 2m plus p minus n over 2m. So we have 1 plus x is equal to 2m plus p minus n over 2m. But let's work on that a little bit. 2m is, of course, by definition, n plus p. So now we have n plus p minus n over 2m. And the n's cancel, and that's 2p over 2m, or p over m. So now we're going to rewrite this equation a little bit. I'm going to pull that m into the equation. I'm going to pull the m into the equation, so I'm going to write it as knp times n over m minus kpn times p over m, and that's x prime. And now, p over m, which is right here, I now know that that is 1 plus x. By the same style of argument, it's easy to show that 1 minus x is equal to 1 minus p minus n minus over 2m. And that's going to be 2m minus p minus n over 2m. And that, when we start substituting m, 2m is equal to n plus p, we have, this should actually, no, that should actually still be a minus there. So this is going to be p plus n minus p plus n is 2n over 2m. So that's n over m is equal to 1 minus x. And now we can substitute all of those in there. So now we take our basic differential equation here. And of course, that should have been over m and over m because we're going to be substituting in. And now we can say x prime is equal to knp. But we said that knp is equal to v e to the ax. And that is going to be multiplied by n over m, which is 1 minus x. And then we have minus kpn times p over m. Well, kpn is v to the e minus ax. That's kpn. And then p over m is 1 plus x. So look at what we have here. We have a differential equation. In the single variable x prime, this is x, this is a constant, this is a constant, that's a parameter, that's x, parameter, x. This is a complete differential equation in terms of those parameters. And now the question is, what is this system going to do? So here's our differential equation. Now the next question is, what behavior does that predict? And it's hard, because those are very nonlinear equations. It's far from obvious what behavior is predicted. But of course, the first thing we're going to do is find the equilibrium points. as always. So we know how to do that. We set x prime equals 0, definition of an equilibrium point. So the first thing we know if we set this equal to 0 is, as I promised you, the v drops out. Just divide by v. So now we're looking for places where 1 minus x e to the ax equals 1 plus x e to the minus ax. And that's still hard. You can't solve that paper and pencil. Those are nasty nonlinear equations. But what we can do is go to the graphing calculator, to CoCalc or whatever we're using, and solve this graphically. Plot these two, and then ask where do they intersect, or just plot them overall as a vector field. So I decided to do it the second way. We're just going to plot this vector field in a classic vector field diagram where x is going to go here and x prime is going to go here. And we're going to show you the graph of x prime as a function of x. Now we're going to take a couple of different values of the parameter a. For example, I'm going to let a equal 0.5, which is a bit of a bandwagon effect, but not a gigantic one. So when a is equal to 0.5, we graph this expression, and it looks like this. That passes through 0. And you see how many equilibrium points it has, namely 1. And then if I ask you stable or unstable, you use the method of linearization. The slope there is negative. This is a stable equilibrium point. And I want to point out that it's a stable equilibrium point at the value x equals 0. And remember that x is defined as the imbalance towards positivity. So when x equals 0, p equals n, which means the two opinions are equally balanced. That's what p equals n means. The number of p's is the same as the number of n's. P and n are equally balanced. That is a stable equilibrium point. The resulting state space is going to look like that. That's x state space with the vector field on it. There is the stable equilibrium. And what this says is that for this value of the strength of the bandwagon effect, there is going to be one stable equilibrium, and it's going to be at a balanced state where negatives and positives are equal. Now, let's ask what happens for a different a. And now I want to plot, let's say, a equals 1.5. And when we plot a equals 1.5, we plot this equation, for a equals 1.5, we get a different shape of curve. The curve now looks like this. And what does that say? Well, notice how many equilibrium points do we have for a equals 1.5? Well, we still have 0, but now we have 2 new equilibrium points at positive x and another one at negative x. And what has happened to the stability of the equilibrium points? Method of linearization. This slope is positive. That means that that equilibrium point is unstable. Let's redraw state space here now. This is 0. The equilibrium point at 0 has positive slope. That means it's unstable. These two equilibrium points have negative slope. That means that they are stable. So look at what we now have. We have an unstable equilibrium point at 0. The center is now unstable. And instead, we have two new stable equilibrium points at all positive or all negative, all negative or all positive. So from the mathematical modeling point of view, we have come up with an interesting conclusion, which is, let me put it in words, if the bandwagon effect is weak, there's only a single equilibrium point and it's stable, and that equilibrium point is at balanced opinion. If the bandwagon effect is strong, and in particular if A is bigger than 1, if the bandwagon effect is strong, the center is no longer stable, and now we have the two extremes are the only stable points of view, are the only stable equilibria of this system. So what is that saying? Well, Lux uses it as a model of a bubble, that is to say an increase, all positives, or a crash, which is the opposite, all negatives. And it's obvious if you're going to go to all positives or all negatives that it really just matters, are you slightly on the left of this point or are you slightly to the right of this point? If you have the slightest little imbalance towards negativity, the whole thing is going to go negative. If you have the slightest little imbalance towards positivity, the whole thing is going to go positive. So this is a model, as Lux says, of bubbles and crashes. But more generally speaking, we can view this as a model of the emergence of political polarization. Because what this model says is you have this feedback term, this positive feedback term here. That is the term that says, I want to be with the majority. What is the strength of my wanting to be with the majority? How much positive feedback is being given to me in my positive or negative attitude? In other words, one of the things you could say would increase the value of A is the emergence of cable TV. Back before your day, when there were only broadcasts, there was only the center. There was only Walter Cronkite. And Walter Cronkite gave you the center opinion. And the center was stable. With the rise of cable TV, there is reinforcement of positive and negative attitudes. Alpha becomes greater than 1, and now we have the emergence of political polarization explained purely structurally by the change in that parameter. So what has happened here mathematically is clearly a bifurcation. A parameter, namely A, passed through a critical point, namely 1, and the number and stability of equilibrium points changed. That's the definition of a bifurcation. In particular, it changed from 1 stable at 0 to 3, a stable, an unstable, and a stable, and that's for the alpha greater than 1. And so that clearly is a bifurcation. Now you see the SUS, the stable, unstable, stable, and you remember that a little bit from saddle node bifurcation, and you go, oh, maybe this is a saddle node bifurcation. But then you look closely and you see it isn't. Because in a saddle node bifurcation, we ended up with an SUS, but the S was always stable. And then as the parameter passed through the critical point, like in the lac operon, you had the birth of a new pair. And the new pair was the unstable and the stable. And that's how you got this. But this is very different. This is not the stable equilibrium remains stable and a new pair is created. The configuration here is the old stable equilibrium became unstable, flanked by two new stable equilibria. Those stable equilibria did not exist before the bifurcation. And the one that was stable has now become unstable. So this is a very different bifurcation. Let's make the bifurcation diagram. So as you know, in a bifurcation diagram, we're going to put the parameter value there. And then we're going to put state space here and draw the location and stability of the equilibria. So if this, let's put a 1 right here. This is A equals 1. For A less than 1, we have a single equilibrium at 0, and it is going to be stable. As A is now bigger than 1, the equilibrium at x equals 0 is now going to be unstable. Conversely, you had no equilibria here for A less than 1. You had no equilibria except that one stable one. But now as A gets bigger than 1, we have a new pair of stable, a new pair of stable. As A gets larger and larger, that thing goes out more and more. And we have this, and we have this. And the resulting bifurcation diagram is called a pitchfork bifurcation. It's not writing well. It's called a pitchfork bifurcation because if you remember what a pitchfork, you remember Grant Wood's American Gothic painting where the old couple is holding a pitchfork. This is a pitchfork on its side. And in a pitchfork bifurcation, what happens is exactly what you see here. A stable equilibrium becomes unstable, and two new stable equilibria are created on either side of the stable. And this is a new animal in the zoo. This is a new kind of bifurcation called a pitchfork bifurcation.